So this is example number 4 for conservation of momentum. So let's consider the previous example that we were working on. We had all these velocities for we had 4 openings. We had flow coming in, flow going out, and we found that these were the vector velocities. We found the unit vectors. Remember, unit vectors are always normal to the control volume. They're always normal, so that's how we found these. And then this is delta S1. This was all given, and this is what we found from conservation of mass. That was the unknown. In this problem, this is not completely true, but let's assume that it's possible to maintain all the pressures, each one of these points completely identical. And if that is possible, then everything is atmospheric pressure. The total volume inside this tank is 10 feet cubed. And basically what you ask for is to find the reaction force at O to hold this entire tank in place. Okay, so before we start that, let's go ahead and define what is the force required equivalent force required of the fluid. So this is the equivalent force of the fluid. And that would be F is equal to F of X, I, F of Y, J. So if I want to find what is the load to hold this in place, and this is equivalent force of the fluid, then the reaction to hold the tank will be R plus F is equal to 0, or R is going to equal to minus F, or minus F of X I minus Fy J. Okay, so this is what we are really looking for, what we are after. So whenever we want to find forces, we want to use the conservation of momentum. Okay, and the conservation of momentum from our lecture notes was given as follows. This is the integral over the region, the volume region of total, the substantial derivative of the velocity, which this is equal to rho F over the volume minus the double integral of P and ds. So now this term right here, if you remember from our notes, it's going to equal to the triple integral of R rho V over the volume plus the enclosed area over the surface V rho velocity times the dot product unit vector over ds. So all this is just this part over here, what we are expanding on, okay? So we know in the problem this is equal to 0 because the problem is steady flow. The problem says that it's steady flow, okay? So then this expression is equal to the double integral of V velocity times the dot product velocity unit vector of ds. This expression right here is equal to that. So let's write all this expression now all together, and we'll get the following expression. And I'm going to write everything. I'm going to equate the whole equation to 0. It's a little bit more convenient to work with that equation in that form. D of S plus R rho of F the volume, this is minus, sorry, plus S P N ds is equal to 0. And we were going to work we're going to call each one of these terms 1, 2, and 3. We work with each one of the terms individually, and let's see, and then we put all the terms back together. Okay? So let's work with term number 1. In term number 1, what we have is the double integral of v rho v dot n d of s. This is summation of I equal to 1, and it goes to 4. Why? Because we got 4 openings. We got 4 flows. 1, 2, 3, and 4. So that's why I'm going to put the 4 there. It goes rho I, vi, this is the vector, vi, the vector, this is a unit vector, delta si. In other words, this whole thing is going to equal to v1 rho v1 dot n1 delta s1 plus v2 rho v2 dot n2 delta s2 plus v3 rho v3 dot n3 delta s3 plus v4 rho 4 v4 dot n4 delta s4. So now let's go and replace all the values in there. Go to our table. V1 was positive 6j, and n was plus j, and s was 1. So we'll plug those numbers inside here. So this is 6j, and get rho. This is 6j dot product with j times 1. Okay, now let's go with the second one. Second one, this is minus 6i, minus I, and this is 1. Okay, so we will replace that in here. Minus 6i rho minus 6i dot product minus I all multiplied by 1. We can add all this, and the second term and the third term will be 6j minus j for n and 4. So this is plus 6j, and this is rho. Remember, all the density is the same, right? This is 1, this is 2. The density is identically the same. So I'm going to change this to rho. That's why I'm doing that. So this is 6j. The unit vector was minus j times 4 plus, and the last one was 6i, positive I, and 2. Replace that in here. 6i rho 6i dot I times 2. Okay, so what you can see here is if we take this dot product here and you j times j is 1, so this all gives you 6 times rho. Minus minus is plus, I is 1, so this gives you 6 times rho. This gives you minus 6 times rho, and this gives you 6 times rho. Okay, so I'm going to go to the next page, next slide, and I'm going to go ahead and work my math now. Okay, so this whole thing is equal to 36 times 1 rho j minus 36 times 1 rho I minus 36 times 4 rho J plus 36 times 2 rho I. Okay, so this is equal to 36 rho J minus 36 rho I minus 144 rho J plus 72 rho I. Okay, so the expression number 1 then is equal to minus 108 rho J minus plus 36 rho I. Okay, so this is expression number 1. Now we found this one. Let's go to expression number 2. Expression number 2 is the body force and body force due to gravity. So one thing that's important to keep in mind here when I'm finding the body force, this is nothing else than rho g times the volume J. This will be a minus sign. Why? Because if you look at your problem, your y is going up. You see your y is going up, but your gravity is really going down. Okay, so it's opposite in sign. That's where the minus sign comes from. And this expression here comes from the fact that you have m mass times gravity, and then mass is nothing else than rho times v, g, and then you can express this rho g v. Okay, this is where this expression comes from. So now we are done with expression number 2. We're going to go to expression number 3. We go to the very last expression now. So it's 3. And the expression number 3 says that double integral of s p dot s summation of I equal to 1, again 4, because we have 4 openings, 1, 2, 3, 4, and 4 flows, right? You can have 4 openings, but only 3 flows. In that case, then it will be 3, okay? And I delta SI, okay? But then you have to add here Fi at the force F. This is the equivalent fluid force. Okay? So this whole thing then is equal to P1 and 1 delta S1 plus P2 and 2 delta S2 plus P3 and 3 delta S3 plus P4 and 4 delta S4. Okay, so I'm going to, and obviously I got the force plus f of x I plus f of y j. So I'm going to replace all these values, remembering the problem that all the pressures were atmospheric pressure. And then your n's come from here. This is j, this is minus I, this is minus j, this is plus I, and your delta s's come from here, okay? So if I replace that there, I get j1 plus p atmospheric minus j1 plus p atmospheric minus j4 plus p atmospheric I times 2 plus fxi plus fyj. Okay, so now I'm going to simplify all this in the next slide. This gives me P atmosphere, pre-atmospheric minus 4 atmospheric J plus Fyj. Put all the J's together. Let's put all the I's together. And then 3 is actually going to equal to this. P atmospheric plus f of x I plus minus 3 P atmospheric plus f of y j. Okay, so this is what we have. Now we're going to go ahead, we're going to put everything back together into this expression. Okay, so I'm going to duplicate this slide. Let's bring it down here. Now we're going to go ahead and replace everything. So what we found from this was 108.36. So this is, I'm going to write it 36i minus 108j. Okay, this is expression 1 minus second expression. This is rho GV. So this is minus rho G volume. This is J. Then this is plus the very last expression that was right here. So that will be P atmosphere plus f of x I plus minus 3 P atmospheric plus f of y. I'm sorry, the I goes outside and the j goes outside. Okay, all of this has to equal to 0. So if I go ahead now, I collect some terms here, doing a little bit of mathematics. Let's go to the next slide. So you have 36i plus 36 plus P atmospheric plus f of x. Combine all the terms in I together and all the terms in j together. Okay, that's what I'm doing in this expression. Atmospheric plus f of y. This is j is equal to 0. Now pay close attention here. The only way this can be 0, since this is an orthogonal axis, remember they're completely orthogonal, so they're really not related to each other. What happens here stays here, what happens here stays there. The only possible way this can be 0 is if each individual of these components are actually equal to 0. Okay, so that would give me two equations. P atmospheric plus f of x is equal to 0. That gives me f of x is equal to minus 36 minus P atmospheric, and P atmospheric is for air is 47.67. This is pound inches squared. Remember, I only have here, this is already embedded here. Everything was multiplied by delta S. You're already multiplying S squared. So it cancels, this gives you pounds. Okay, so this whole thing gives you minus 57B pounds. Now let's go to the next expression. Okay, and the next expression says, the next expression gives you 108, this one right here. Okay, 108 plus rho GV minus 3 times P atmospheric plus Fy is equal to 0. So from here, Fy is equal to 108 minus 0.00237769. This is rho. multiplied by 32.2 times 10 plus 3 times 14.67. And if you do the math here, 108 minus 0.7654 plus 44.01. This gives you 151.24 pounds. So the force felt by the fluid is the force felt by the fluid is minus 5067I plus 151.24 J pounds. But what we are looking for is the reaction, and the reaction is minus F. Okay, so this is 50.67 I minus 151.24 J pounds. So this is the reaction force that we are looking for, and this concludes our example number 4 on momentum.